Chapter 1.10, Mathematical Modeling and Variation. So our goals are we're going to use mathematical models to approximate sets of data points, write mathematical models for direct variation. We're going to write direct variation as an nth power, write models for inverse variation, for combined variation, as well as for joint variation. So example 1, we're going to use a mathematical model. The table shows the population Y in millions of the United States from 2008 through 2015. So we have this data. In 2008, it's this population and so forth. So we have a linear model that approximates the data, and that is this equation here, when time is between 8 and 15, 2008 and 2015, where t represents the year, with t8 corresponding to 2008. We're not going to plot the actual data, but we're going to go ahead and plug in the values into the model to see how closely the model represents the data. So if you plug in 8 into this equation here, and you just plug in each and every one in order to get the points, and so what we would get is 2008, we would get 304.3. 2009, we get 306.8. For 2010, we get 309.2. 2011, we get 311.6. 2012, we get 314.1. 13, we get 316.5. And 14, we get 318.9. And 15, we get 321.4. So what we're going to do is we're going to see, does this model closely represent the data? So we look at these numbers here, then we look at the actual population in numbers. Notice that they're all very close, 304.1, 304.3, 306.8, that's exactly the same, 309.3 to 309.2. So we can safely say that the model is a good fit for the data. Okay, so the model is a good fit for the data. Okay, so go ahead and try the next example. You have the order pairs given this median sales price in Y and thousands of dollars of new homes sold in a neighborhood from 2009 through 2016. We have a linear model approximating the data is here, and t represents the year, t equals 9 corresponds to 2009. We don't need to plot the data, but just plug in the values and see how close does it come to our values here. Pause the video, try it out. So if you tried it out, you would have gotten these values. And notice again that they're very close to the values that were actual. And so we can say that the model is a good fit for the data. Let's take a look at direct variation. There are two basic types of linear models. The more general model has a non-zero y-intercept. So we know this one. And the simpler model, though, has a y-intercept of 0. We're going to use k as our constant of proportionality. So the statements below are equivalent. Y varies directly as x, or y is directly proportional to x. And so we can write this as y equals k times x. It's directly proportional to x. So let's try this in example 3. In Pennsylvania, that state income tax is directly proportional to gross income. You work in Pennsylvania and your state income tax deduction is $46.05 for a gross monthly income of $1,500. We're going to find a mathematical model that gives the Pennsylvania state income tax in terms of gross income. So in order to fill this out, let's try to write things that we know. We know that we have our state income tax, so we'll write state income tax, and that's going to equal the income tax rate times the gross income. So let's add some variables in here. Say income tax, we're going to label that as our y, income tax rate will be our k, and the gross income will be x. So we're given your state income tax deduction is $46.05, and the gross monthly income of $1,500. So we plug this in. We really want to try to figure out what is our k value here. Oops. What is our k value? So to do that, we just plug in what we have. So Y, state income tax, that is 46.05 equals K times the gross income of $1,500. So then we solve for K. So here that K is approximately 0.0307. So we take that and we plug it in, and we have Y equals 0.0307 and then times X. So this is the mathematical model that gives the Pennsylvania state income tax in terms of gross income. Okay, so we're just trying to find that model. Let's do direct variation as an nth power. Another type of direct variation relates one variable to a power of another variable. Again, we're going to use K as a constant of proportionality. Direct variation is an nth power. The statement below are equivalent, so y varies directly as the nth power of x, or y is directly proportional to the nth power of x. So this is y equals k times x raised to the nth power. So let's do an example. The distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. During the first second, the ball rolls 8 feet. So we're going to write an equation relating the distance traveled to the time. So right now we have distance equals k times t squared. So distance we were given was 8 feet. So we can plug that in. Distance equals 8 feet. We're trying to figure out what k is. And then time, it says the first second. So that is 1 squared. So therefore we know that k equals 8. So let's plug that in here and get our equation relating the distance traveled to the time. So that is distance equals 8 time squared. So then we need to figure out how far does the ball roll during the first 3 seconds. So we just plug it in. Distance equals 8 times 3 squared. So that is going to be 72 feet. Let's do inverse variation. The statements below are equivalent. Y varies inversely as x, or y is inversely proportional to x. So that is y equals k over x. So we're going to find an equation. In this case, we're talking about demand and price. Example 5. A company has found that the demand for one of its products varies inversely as the price of the product. When the price is $6.25, the demand is 400 units. So we need to write an equation relating the demand and price. So demand will be D equals K over price, right? Inversely proportional. So given that the price is $6.25 and demand is 400 units, let's plug that in. So 400 equals K over $6.25. So you solve, K is going to be 2,500. So our equation is going to be D, the demand, equals 2,500 over the price. So now B, we're going to approximate the demand when the price is $5.75. So we just plug it in. Demand equals 2,500 over $5.75. So the demand, when you plug it all in, is going to be approximately 435 units when the price is $5.75. So let's try combined variation. Some applications of variation involve problems with both direct and inverse variations in the same model. These types of models have combined variation. So let's try this example. A gas law states that the volume of an enclosed gas varies inversely as the pressure and directly as the temperature. The pressure of a gas is 0.75 kilogram per square centimeter when the temperature is 294 Kelvin and the volume is 8,000 cubic centimeters. So we need to write an equation relating pressure, temperature, and volume. So we know that volume equals K, and then it says inversely as the pressure, so inverse, the pressure will go in the denominator, and directly to temperature, so that'll go in the numerator. So we're given certain information. We know the temperature equals 294 Kelvin, and we know that the volume is 8,000 cubic centimeters, and we know that the pressure equals 0.75 centimeters squared. So we're going to plug this in to figure out what our K is. We need to figure out K. So volume equals 8,000 equals K times 294 over 0.75. So when you multiply 0.75 to both sides, divided by 294, K is going to equal 1,000 over 49. Okay, you would reduce, of course. You would get like 6,000 and you have to divide. So now we write our equation. So volume equals 1,000 over 49 times T over P. So we're going to find the pressure when the temperature is 300 Kelvin and the volume equals 7,000 cubic centimeters. So we'll plug it in. We have 7,000, this is our formula, equals 1,000 over 49 times 300 over P. So to solve for P, I'm going to multiply P to both sides, then divide by 7,000. So it would be P equals 1,000 over 49 times 300 over 7,000. And you would plug that in, the pressure is going to be approximately 0.87 centimeters squared. The last thing we'll do is joint variation. The statement below are equivalent. Z varies jointly as x and y, or Z is jointly proportional to x and y. So we write this as y equals k times xz. The simple interest for an investment is jointly proportional to the time and the principal. After 1 quarter or 3 months, the interest on a principal of $5,000 is $43.75. So we need to write an equation relating the interest, principal, and time. So that's going to be interest equals k times principal times time. In this case, we know principal is 5,000. We know that the interest is 43.75, and we know the time is 3 months, so we're going to do it in a year. So we're going to say that that's 1 over 4. So you plug it in, you have 43.75 equals k times the principal 5,000 times 1/4. So when you solve for k, k is going to be 0.035. So our formula is I equals 0.035 P times T. So we're going to find the interest after 3 quarters, so that's 3/4 is our time. So you plug it in, interest equals 0.035. The principal is the same at $5,000 times 3 over 4. So when you solve for that, you'll find that the interest is going to be $131.25. Thanks for watching.